AI vision is getting a lot more practical. Not just smarter, but faster, lighter, and easier to deploy without retraining giant models from scratch. The big shift is that careful token selection, cheaper aggregation, and even frozen video diffusion priors are starting to beat brute force architectures on real geometry tasks. That matters because long videos, stereo, and hand motion all collapse under compute pressure in the real world. Here's what these results say about where efficient perception is headed and what techniques are actually winning. Let's explore the first paper, Good Token Hunting, a Hitchhiker's Guide to Token Selection for Visual Geometry Transformers. Good Token Hunting, developed by researchers at the University of Toronto, the Vector Institute, Google, and the Technical University of Munich, reframes acceleration of visual geometry transformers as a constrained key value token selection problem inside global attention. The paper shows that a two-stage hierarchy is decisive. First, interframe selection keeps a diverse set of anchor views using a K-center objective approximated by greedy farthest point sampling. And second, intraframe selection applies layer adaptive pruning guided by global attention entropy, replacing the earliest layers with local attention and using more conservative downsampling where attention spikes on 7 scenes, neural RGBD, TUM dynamics, and BON. This training-free GoToHunt plugin consistently matches or improves base model quality while scaling much better than fast VGGT, sparse VGGT, CoMe, light VGGT, and Speed 3R. The clearest result is on 500 frame scenes, where it cuts VGGT inference time from 288 0s to 41, 2s, an 85% reduction, and it also avoids sparse Pi3 out-of-memory failures on long bond sequences. Across tasks, the method preserves camera pose, 3D point reconstruction, and video depth accuracy with near-linear time growth, showing that careful token selection can outperform brute force token retention in long context 3D vision. Let's explore the second paper, Light Any Stereo V, 2 faster and stronger efficient, zero-shot stereo matching. Light Any Stereo V2, or LAS2, from Imperial College London, reframes efficient zero-shot stereo matching around deployment reality rather than MAC counts alone. The paper replaces the heavier 3D aggregation used in prior LAS with a pure 2D cost aggregation pipeline built on FasterNet, then trains a family of feed-forward models, LAS2, S, M, L, plus an iterative LAS2H variant. Its 3-stage training recipe combines supervised learning on 1, 8M synthetic stereo pairs, self-distillation with feature alignment, and pseudo-labeled adaptation on 0, 5M real-world unlabeled pairs, where pseudo-supervision is cleaned by left-right consistency, edge masking, sky masking, and error clamping. On 4 zero-shot benchmarks Kitty 2012, Kitty 2015, ETH3D, and Middlebury LAS2, M reaches 2.88D, 1 on Kitty 2012, 3.61D1 on Kitty 2015, 2.59 BAD1 on ETH3D, and 5.47 BAD2 on Middlebury, while running in 8.1 milliseconds on H, 200 and 101 milliseconds on Orin. LAS2H further improves to 2.64 D1 on Kitty 2012 and 3.31 D1 on Kitty 2015, with 15.1 milliseconds on H, 200 and 344 milliseconds on Orin, outperforming Fast Foundation Stereo in accuracy while remaining much faster. The ablations show that FasterNet is the best practical block choice and that the final training stage drives the largest gain, reducing LAS2, M's error substantially over stage 1 alone. Overall, the paper argues that efficient stereo can now be both strong and deployable without relying on foundation model priors. Let's explore the third paper, the surprising effectiveness of video diffusion models for hand motion reconstruction. VidiHand is a new hand motion reconstruction system that repurposes the 1.3b parameter WAN2, 1 VACE video diffusion model, an Alibaba Group backbone for 4D two-hand pose recovery from Egocentric video. The key idea is to fine-tune only the VACE branch with a hand overlay rendering objective, first on EgoDex joint overlays, and then on Arctic and Hot 3D Manomesh overlays, so the diffusion model learns hand-aware scene features without losing its general video prior. A 37M parameter dual branch decoder then reads a single mid-layer activation, specifically die T layer 15 at denoising step 0.7, and combines a hand token branch, a 2-1 joint heat map branch, mutual cross attention, and a mixed projection camera translation solve to recover manopose and metric scale 3D translation with no detector, infiller, or test time optimization. On Arctic, VidiHand reaches 0.997 frame accuracy, 21.668 mm MPJ-PEP, 12.407 px EPEP, and 3.183 mm frame 2 jitter. On Hot 3D, it reaches 0.948 FACC and 3.741 jitter. On Held Out HOI 4D, it reaches 0.984 FACA and 4.01 jitter, ranking first on 8 of 9 metrics. Ablations show that the full decoder improves Arctic FAC from 0.976 70.9829 in reduced variance to 0.9979, and removing acceleration smoothness raises jitter from 3.42 to 3.88, confirming that the Diffusion prior supplies both occlusion robustness and temporal stability. That's a wrap on today's AI paper highlights. Thanks for watching.